All right, two different things today. Both of them look like this. One of them we're going to factor out some stuff and it's going to cancel. And one of them we're going to factor out some stuff and it's going to cancel. Yeah, it's nice. But we're going to factor it in a little bit different ways. All right, so the first one is we're going to factor out monomials. What's a monomial? Good. It's a number it's usually a term with just one one term in it. Oh, missed. Later on, we're going to factor binomials. We're going to factor out binomials. All right, so anyway, help me with this right now. Take a look at the top. Tell me something that the top two numbers, the top two terms have in common. They have 7 and x. They can both be divided by 7, and they each have x to the first. And we can't take out more than x to the first, right? If we could, then we would take out as many as we can. So here's what would be left over. It's like we're undistributing, right? Tell me what would be left over in this first spot. 2x to the second? Just 2x, right? Because we took one out, okay? How about the last part? Good, it's 1. Remember, we're going backwards from distributing, right? So in order to be correct, I can always check to see if I'm right. So if I do that, I'd get 14x squared plus 7x, right? Which matches where we started from, okay? So that's one way to check yourself. Now here's the point of today. There's nothing to factor on the bottom, but we notice that essentially what we have is x divided by x. And we would call this 1, right? It's also cancels, right? That's what canceling means. So canceling means something divided by itself. What else can we reduce? 7 and 14, right? Okay, what's 7 over 14? It's a half, right? So this turns into 1. This turns into a 2. So we're left with this new fraction, this new reduced fraction like that. Can I cancel those 2's right there? No, I can't, because there has to be a common factor of a 2 up top, okay? I can't take a 2 out of this one but not divide this by 2 also. I can't do that. I could write it like this. I could do that and say that it's x plus a half. I could do that, but we're not going to. We're going to leave it just like that. All right, so that's our answer up here. Whoa. And then down here it says this weird little statement, but we've answered this question before. Which of the values of x make the expression undefined? All right, in order to answer this question, let's go way back to the beginning. Tell me what can go wrong when certain numbers are in fractions, and what's that number in a fraction that can cause problems? Not 9. No. Talking about one very unique number, 0. Where could there be a problem? Okay, you could get 0 on the top, but that's the number. But you could plug 0 in somewhere else here, and you would have an error on your calculator. On the bottom, right? If you put a 0 on the bottom here, for example, we said, hey, x equals 0. And we plug it in there. I want to erase our work here real quick. It would say whatever the top is. Well, it would actually be 0, but whatever that is. And then divided by 0. Can you divide by 0? No. So one thing that would make it undefined would be 0 right there. 14 times 0 would be 0, correct? Okay, some other examples of how to answer this. Let's say we ended up, or sorry, not ended up, but let's say in the beginning you had something like this going on. Let's say it was x plus 1. What number, when you plug in there, would make it equal 0? Yeah. We would say that x equals -1 would make it undefined. So what we're trying to do is we're trying to figure out which one of these choices, if you plugged it in, would give us a fraction that would be undefined. As in, you plug it into the fraction and it won't work on a calculator. Okay? And it would be this one right here. -14, anything else right here is okay. We could all plug those in and we'd get some kind of number spit out of it. But 0 is the problem right there. All right, let's do another one. This one, it's going to ask you which one of these students is right or wrong, or maybe they're both wrong, maybe they're both right. Takumi and Kaliska manipulated the rational expression. The responses are shown below. So let's just look at their work and see if they're right. We can just check it, couldn't we? Okay, so we can do this. Let's see if Takumi is right. What if we distribute this back? This first part would be -9y squared. The second part would be -3y. That matches the top, doesn't it? Okay, the second part, -6y squared minus 6y. Takumi's is correct, right? That's correct. Doesn't say simplify, it just says manipulated. They just changed it. All right, now, Kaliska. Is Kaliska correct? Also. In other words, Takumi is right. We know that. What happens if we cancel the y's and then we reduce this? What's -3 over -6? It's a half, right? Negative divided by negative is a positive. 3 over 6 is a half. The problem is Kaliska has something that's kind of weird looking. It has 3y plus 1 over 2y plus 2. Now, let's take a look at Takumi's again. Let's keep going. If we simplified this, we'd have a half right there, right? Is this the same as Kaliska's? Look carefully. What I really should do is use parentheses around this. What happens if I distribute this 2? Oh, it matches, doesn't it? And how about the top? It's just a 1, so it stays the same. So is Kaliska also correct? Yeah, Kaliska was actually simplified. And then she distributed in the bottom there. So both of them are correct. All right, now they're going to really mess with you on these. There's times when they're both wrong, and they're both going to look really close to the same thing. So be careful. All right, last one on this one. Help me. What does the top two have in common? Z squared. That's the greatest common factor. That would leave Z plus 1, right? That's Z to the first. That's why there's 1 left over. How about the bottom? Whoa. Yep, 17Z squared. 17 goes into 34 and 51. So we've got 2Z. How many times does 17 go into 51? 3. Yep, that's all right. So it's 3. These two cancel all the way, right? There's nothing to reduce, and we have our answer right here. So Z plus 1. Z minus 3. Whoa. All right, now, we have to answer this down below. Now, imagine before I canceled this stuff. So let's take a look right here. If I plug in 0 right there, isn't that going to be a problem? Take a look at it. It's 0 squared. times 17 is 0, and 0 times anything is 0. So this is a problem, right? It had a common factor of z or z squared on the bottom. That's going to be one of your answers. But guess what? We have another thing to look at here. What would make this equal 0? So I'm thinking to myself, what makes 2z minus 3 equal 0? Now, we've seen this sort of thing before when we factored and we looked for solutions. I said, find the opposites of both, right? So imagine it was a factor and I said, hey, what's the solution? How would you answer that? Positive 3, and then do what with the 2? Divide. Not turn negative. All right, so what we do is we're doing the opposite. All right, imagine if I just solved this equation up here. How would I get z by itself? What would I do? Add 3 and do what? Divide by 2. That's another way to think of it. So this would make the bottom also equal 0. So I have 2 answers this time. Okay, there we go. I'm going to let you get started on this one, and then we'll come back in a little bit and do the second one. It's the same concept, except we're going to be factoring like with 2 sets of parentheses in the binomials.